Should we close this door?
Yeah.
Okay, I guess we'll get started. Hello, everyone. Welcome to Beyond Linear Decoding, an introduction to deep learning. If this is not the course you're looking for, you might want to leave now, just like an airplane. But if it isn't and you are here, then perhaps it's a happy accident, because I think that this will be a very fun and informative afternoon. I'm Pamela Douglas. I'm from UCLA and UCF. I'll be motivating this problem of why should we learn about deep learning as neuroimagers. After me, there's two speakers who are amazing. I highly recommend following both of them on Twitter, Anisha and Andrew Doyle. They both have some really exciting work. Andrew Doyle is a software developer at the MNI, works with Alan Evans, and Anisha is a postdoc at University of Washington. After that, we have Pim, who's going to bring together all of this information that you've then learned and show how you can apply it to neuroimaging data for parcellations, for example, in neurodevelopment. After that, we have Chris Beckham, who I actually first met on a bushwalk in New Zealand when I was visiting the University of Waikato. And he's now at the Montreal Institute for Learning Algorithms. And he works with Chris Powell and also collaborates with Yoshua Bengio. So he'll be teaching us about GANs, generative adversarial networks. And finally, we're going to wrap up with Alex Binder, who's going to tell us about the newest and latest approaches for interpreting deep learning algorithms. Alex is a professor here in Singapore. He's local, and I was introduced to him by Klaus Robert Müller. And Alex wins awards for best paper at CVPR and some of these very prestigious machine learning conferences, so we're very, very excited to have him. So, beyond linear decoding. So this is the type of slide and image you may have seen if you're in the neuroimaging field. There's two classic approaches that we use to study functional neuroimaging data: encoding and decoding. Both of these study stimulus-response dependencies, but use inverse directions of inference. And the important point here is that encoding models, which tell us about how activity varies when there are changes in the outside world or stimuli, are at the first stage analyzed independently from a mass univariate approach. And spatial dependencies are introduced later, during later stages of analysis, through things like Gaussian random fields. Decoding uses the opposite approach, where it takes the response patterns and tries to make predictions about the stimuli or the outside world. So many, many years ago now, 13 years ago, this paper came out by Kamatani and Tong, and this caused a huge amount of excitement in the neuroimaging field, because what they were able to do was decode orientations from visual cortex. And previously, this type of information had eluded the traditional encoding analysis. So people became very excited that we could somehow study these patterns of activation using decoding approaches that inherently take voxel patterns of activity and collaboratively analyze these data in combination. And so ever since that paper, the popularity of decoding approaches has grown quite a bit, as shown by this Etzel paper here. So the idea is that somehow, by studying the voxels in combination, we might learn more about the patchy functional segregation of the underlying neural code. So common questions we ask with decoding models are: can we perform decoding using response pattern activations, which is probably the most common? Which stimulus items elicit patterns that are distinguishable? Can responses be used for brain-computer interfaces? And can we predict group membership, or possibly a disease group versus a healthy group? So there are many types of classifiers, each with their own inductive bias. But linear classifiers have by far dominated the neuroimaging literature. So why is this? I think there's about 4 reasons why. The first is that linear decoding approaches are computationally efficient. The The second is that they're thought to be very easily interpretable. Third, they often are thought to yield comparative prediction accuracies. And lastly, they're suitable for examining patterns of activity. So here today, I'm just going to go through a couple of basics of linear decoding approaches, perhaps a few reasons why you might want to move beyond linear decoding, and eventually towards testing fully computational theories. So here's just a brief summary of the typical decoding analysis flow. We have voxels in our input space. These are mapped to feature space. We then perform classification, and this furnishes us with both accuracies as well as feature weights. So now I'm just going to take you through the absolute simplest case where we have two features, we'll call them voxels, and two classes. But I'm going to demonstrate this on a very important problem. Chihuahua or blueberry muffin. This is a problem I've discussed at some length with Gael Verico and Alex Gramfort, who have been involved with the development of NiLearn, which is a fantastic toolbox, but does, at least the last time I checked, rely mostly on linear decoding approaches. So let's say we have two voxels. In the blue voxel at the top, we have neuronal signal plus some measurement error. In the second, we have some noise. So in the first voxel, it has some signal, and so this can help us clearly differentiate between whether we have a chihuahua or whether we have a blueberry muffin. In the second voxel, we have almost zero information, and we're going to assume just in this very simple case that the covariance between the two is actually zero. So I like to think about these types of things geometrically. So let's take a look at this. In this very simple two-class case using linear discriminant analysis, we might get data that looks something like this, assuming equal variances. So if we take this data here and we project it onto the noise voxel dimension, you can see that there's hardly any information in X2, as one might expect, because that's just a noise voxel. If we take this same data and we project it onto the first voxel, which is our neuronal signal, you can see that this yields a reasonable prediction and discrimination between the two categories. And the Bayes optimal classifier turns out to be at this mean between mean chihuahua minus mean muffin. So if we take this plane, this hyperplane, in the case 2D case it's just a line, but there's a W vector, or the weight vector, which is orthogonal or perpendicular to the discrimination boundary. And if we take this W vector and project it onto each of the two different dimensions, you can see, just as you might hope and expect, there's a very strong weight assigned to the first voxel, which contains neuronal signal, and very little information assigned to the noise voxel. So this is exactly what we would want, and it's a very happy condition. We can separate chihuahuas and blueberry muffins without a problem. Let's take this same exact case, chihuahuas, blueberry muffins, but now we have this pesky noise, which is covaried between the two channels. So now our covariance between X1 and X2 is not equal to 0. So it's probably worth noting that this noise could be measurement noise, it could be physiologic noise, artifacts, or it could just simply be signal that's related to a brain process that's not currently under study. So in this case, we might get a slightly different geometry. We might get something that looks like this. In this case, the discrimination boundary is once again orthogonal to the weight vector, and in doing this, you get a better class separation than you would just in the X1 category, in the X1 dimension. But if you take this W vector and you look at the strength of that vector in the X1 and the X2 dimension, what you end up finding is that a stronger weight gets assigned to the noise voxel than the informative voxel. So this is disappointing, and this may happen quite often, or it might not. It's unclear in real data, but I can think of many instances where we might have shared noise between voxels. So Haufe and colleagues came up with a nice fix for this, where we simply take the inverse transpose of the wave vector, and then that gives us what's called activations or activation maps. So this fix is actually quite nice, and it works very well. And even though I've shown this for linear discriminant models, the same essential principles apply for other linear models, for example, linear support vector machine, which is one of the most commonly, I think, applied in the neuroimaging field. So because of this, presenting weight maps as results, I think, may lead to an implied interpretation that these results in some way resemble encoding results. But this is just in the case when the voxels contain some amount of mutual information. But what if the features are independent? So features, there's all different ways to extract features from functional MRI data. We can use voxels, searchlights, functional connectivity matrices, graph theory metrics, effective connectivity. All of these have been used. But this last category here, principal component analysis, or independent components, can also be used. And in this case, we expect that the feature dimensions will be independent. So I've done a lot of work with Ariana Anderson at UCLA on using independent components as classifier dimensions. So for example, we had this nice data from Sam Harris, who asked people to answer these questions, things like, do you own a toaster oven? And people would respond either, yes, I believe I do own a toaster oven, or no, I disbelieve that. I don't own a toaster oven. And so we use this data. Here are the general linear model univariate results. And we tested a variety of different classifiers using IC features. So we tested K-star, which is similar to fNIRS neighbor, naive Bayes, decision tree, support vector machine, eta boost, and random forest. So at least in this case, we found that linear support vector machine performed the worst out of the other classifiers tested. So I think this result illustrates the importance of testing multiple models, because there's this thing called the no free lunch theorem, Wolpert and McGreedy, which suggests that no one classifier will work universally across all domains. So in thinking about this problem, it's unsurprising in some sense to think about how certain results have found that there's little spatial overlap between the mass univariate approach and the MVPA, approach. However, in terms of using ICs as dimensions, I did find a considerable amount of spatial overlap between the univariate approach and the independent components that were used in decision trees. So one of the things that's interesting about these ICs is that, just as a side note, we found that including independent components that were purely noise, that were, say, from the CSF, somehow or another still boosted the classification accuracy. So I found this result very perplexing for a long time until I started to realize that actually noise can help boost classification accuracy quite a bit. And so if this topic interests you, I suggest perhaps coming to the morning workshop that we're hosting the last day, which is called Good Noise and Neural Computation. So another problem that exists with interpretation of linear classifiers is this issue with redundancy. So it turns out that when you have lots of redundancy, which may be the case in the cortex, because the cortex is thought to have a certain amount of spatial similarity that's extended to prevent fault tolerance, for example, for fault tolerance. So redundancy can cause the importance of weights to be shared across multiple voxels. So one way to get around this is to use feature selection. And the importance of feature selection has been debated to some extent in the neuroimaging community. So there was this nice paper by Chu et al. In 2012, where he suggested that feature selection really wasn't that important. But Wesley Kerr reanalyzed that same data 2 years later and found that, in fact, feature selection was quite important. And in my own experience, I participated in this thing called the ADHD 200 machine learning competition a few years ago. And we generated something like 100,000 features. We used feature selection and pared it down to, say, 500. But it was, Even after that, we had a great classification accuracy, and I think our team was third place, but the winning team used only a few demographic features. And so if you put all this work into generating 100,000 features, and then the winning team only used a few demographic features, then you may have been as frustrated as I was. So another way to reduce redundancy inherently is through regularization. But unfortunately, regularization doesn't improve the interpretability of weight maps. So Gael Verico has said this very nicely when he says, voxel selection by the L1 penalty on brain maps is unstable because neighboring voxels respond similarly, and the L1 estimators will choose somewhat randomly which of these correlated features to weight. So in this column here under lasso, you can see that when there's signal in two voxels, that the weight gets assigned somewhat randomly to each voxel. So this may or may not be important to you if all you care about is classification accuracy, but if you're trying to predict, say, whether a voxel belongs to a tumor and you're going to resect the tumor, it may be very crucial that you get the entire tumor. And so using this technique, you may run into some serious problems. So there's this other case where we have not just redundancy, but also noise and also regularization. And this problem was explored very nicely in the Stefan Halfa paper from 2014. So say we have a signal, which is on the top, and a distractor pattern. If we take these and we run a very classic linear approach and we get this weight map, what you'll find is something that looks like patchy functional segregation. It looks like the weight map itself is patchy and somewhat random. And if you use an L1 regularizer on the weight map, what happens is you lose information. So that's unfortunate. However, if you take that weight map and project it back into activations, you do recover most of the signal, and then applying regularization to the activation maps can actually help you recover a pure version of the signal. So it seems that imposing sparsity on the activation maps can actually be helpful. So in extreme cases, if you vastly violate this Gaussian assumption, then it turns out that certain noise profiles that may be residual even after pre-processing in functional MRI may corrupt this activation recovery. But for the most part, this ability to recover the signals using the activation approach suggested by Halfa works very well. But it should be noted that noise, as I mentioned, could relate to another brain process which is under study. And in this general case of recovering the activations, we have to understand not just the data covariance, but also the covariance of the latent factors that are under study. And so Russ Poljak in 2006 pointed out this problem with interpreting encoding results which exists called reverse inference. So essentially, we shouldn't make inferences about the hidden cognitive states under study because we're not entirely clear just because you give someone a particular stimuli that that cognitive process is actually engaged. And so a similar analogous result is the case for the decoding approach as well. So one needs to be careful in terms of the interpretation of decoding results in this same fashion. So overall, you're pretty safe interpreting just your classification accuracies, but there's a few tiny caveats that might be relevant to your work, which is if you're comparing accuracies between different brain regions, this could just simply be an artifact that reflects fMRI's ability to sample that region. So there's differences in the hemodynamic response function that vary characteristically across laminar layer, for example. There's some great work by Peter Koopmans which shows this, that more superficial layers of the cortex actually tend to have a stronger magnitude of response. And also Wu and Maranazzo have done this really nice work using Granger causality that shows there's very characteristic differences in terms of delay time. So just like with any other approach that you use that includes encoding, if you're going to apply this canonical double gamma hemodynamic response function, the HRF, that's essentially just filtering your data and expecting that particular pattern to exist. And that exact shape is not necessarily representative of the particular brain region that you're looking at. So why linear? And why beyond linear? So coming back to these few points earlier, are linear decoding approaches computationally efficient? I would say yes, absolutely. Are they easily interpretable? I think just like with any other method, you should use great care when interpreting your decoding results. Definitely try and use the activation pattern method. I would avoid presenting weight maps as your results in papers moving forward. This idea that they often yield comparable prediction accuracies, I don't think that that's true, especially now that we have all of these amazing deep learning techniques that you're about to hear about. I think that those completely destroy linear classifiers at this point, for the most part. But if a linear model does work just as well as a very complex deep learning model, then you might choose the linear model based on certain criteria, in AIC or BIC, for example. And then lastly, are linear models suitable for examining patterns of activity? Well, actually, as it turns out, you can take the dimensions of a linear classifier and permute the dimensions. And all that really does is permute the weights. So in some sense, linear decoding approaches are essentially agnostic to the spatial information. And deep learning approaches that are suited for computer vision take these spatial dependencies into account in much more complex and fascinating ways. So you probably think I got this off of Reddit. But actually, I got this because this is the first reference in the GoogleNet paper. So if you've read this paper, then you'll see that the first citation is this meme from the movie Inception. We need to go deeper. So lastly, the last reason why we should maybe consider going deeper is Nico Kriegeskorte has pointed out in a number of papers that deep learning approaches actually serve as a very rich model for understanding the processes in the human brain. And even though to some extent the biological plausibility of backpropagation, for example, has been debated, these models still serve as a very rich model for different cognitive processes. So without further ado, we'll move on to learning about deep learning models. I will post all of the key references from this talk up on Twitter, and also I have a postdoc position available in case anyone's interested. Thank you. Andrew?